Related rates in Calc 1 are kind of how you take point A and point B and use them to figure out point C. Because as we've been practicing things, we've had something like a y equals, even let's just say ln of x. And then when we take the derivative, well, we're comparing x and y, and we say like y prime is going to equal 1 over x, and then, whatever chain rule we have here, depending on what's going on. But what if we have data that doesn't just compare one to the other? What if we have some kind of interconnection here? And like when I look at this problem, it's exactly what I'm seeing. It says air is being pumped into a spherical balloon so that its volume increases, which means a change in volume at a rate of 100 cubic centimeters per second. Now notice something. This is in seconds. So this is a dV dt, change in volume versus a change in time. I'm sure we would agree on that. And they say, how fast is the radius of the balloon increasing when the diameter is 50 centimeters? So how fast? That sounds like a time. So change in the radius and a change in time. They want to know what that is. And they tell you r equals 25. Don't miss that because it's a diameter of 50. Ooh, that was close. So how would I go about doing this? Well, the volume of a sphere is something they expect you to know, so we'll use that formula. 4/3 pi r cubed. Now notice something, there's no time element here. There's no time element here. That's not good. We need time elements. We can take dv dr. We can take the derivative with respect to the radius, bring the 3 down, you get 4 pi r squared. That's all well and good, but how does that give us dr dt? Well, the only way that we can achieve that would be by looking at dv dt and doing some algebraic magic. Because what if I said this is dv dr, so we know dv dt and we have a dv dr, so let's see what we can do here. We can do a dv dr, and to get rid of this dr, we're going to need a dr on top, and to get a dt, we'll need a dt here. So that's exactly what they want here. What we're doing here is we're comparing a third variable to discern how the first two are related to each other. That's what related rates is in this particular work. So dv dr we found is 4 pi r squared. dr dt would give us the dv dt. Yeah? So what did they give us? Well, they gave us some information. They told us 100. So we can say 100 equals 4 pi r squared dr dt. And we know r is 25. Well, 25 squared is some crazy number. I want to say it's 625. That's not even close, is it? What's 25 times 25? Do you know that off the top of your head? Should be, I want to say it's 625, still feels right to me. So if I was to multiply that by 4, it should be about 2,500. So I'd say 100 equals 2,500 pi dr dt. And we would just take 100 and divide by that, or we could just cross this off like this. And we would say dr dt equals 1 over 25 pi. And then can you tell me the unit? Because it kind of matters, doesn't it? It kind of matters. Well, what was r? What was it measured in? Centimeters per second, because we're changing time. So this would be the answer for this. But the thing that you want to observe here, and then you could compute this with a calculator, it's like 0.013 or something centimeters. That's not what matters. What matters is this execution right here. I want you to stare at this until you get it, okay? dv dt is something they gave you. dv dr is something we can figure out from a basic formula. That allows you to find dr dt. You see how these would cross out and it would match here. So your job with related rates is to connect the dots with different derivative matches. And we're going to do a lot of problems to try and play around with this because there's so many cool examples. Okay, in this case, you took a balloon that's inflating and you were able to learn information about it. So let's go into the problem set and see what we can find.